This month's synoptic chemistry video is looking at hydrogen bonding. In particular, we're going to look at what hydrogen bonding is, how to spot it, and the kind of questions that you get in a real range of different parts of the chemistry syllabus. So that's the whole point of this being a synoptic video, is that hydrogen bonding comes up in lots of different questions in lots of different contexts. So we need to start with what is hydrogen bonding. Hydrogen bonding is a special example of a type of permanent dipole. So permanent dipoles occur when there is a difference in electronegativity between two covalently bonded elements. Hydrogen is the least electronegative non-metal. That's why it tends to form positive ions when it forms ions. So when hydrogen is bonded to a very electronegative element, such as oxygen, the bond is really very strongly polarized. And that is partly because of the very large difference in electronegativity, but also if we consider that we're pulling electrons away from a hydrogen atom. Now a hydrogen atom is just a proton and an electron. So if you pull the electrons away from hydrogen, you're left with just a bare proton. There's no shielding because there's no inner shell of electrons. And this has the effect of forming extremely strong attractions with the negatively polarized oxygen on another molecule. And in fact, what's really happening is the lone pair on that other oxygen atom that is attracted to the hydrogen, it's almost as if it's going to start to form a dative covalent bond when a lone pair gets donated to another atom. Now it can't do that because the hydrogen is still bonded to the other oxygen and there is no orbital to accept another pair of electrons there. So it's not a dative bond, but it's a very strong intermolecular force. So hydrogen bonds have around 5 to 10% the strength of a covalent bond, and that is very significantly strong compared to other intermolecular forces such as instantaneous induced dipoles or London forces, van der Waals, they're all the same thing, or normal permanent dipoles. So we need to be able to identify where hydrogen bonding occurs in a compound, and we need to look for just very specific things to be present. You need to have at least one hydrogen, of course, but that is not enough. The hydrogen has to be directly covalently bonded to a nitrogen, an oxygen, or a fluorine atom. Now, if you look at these elements on your periodic table, they're in the top right-hand corner, and that means that they are the three most electronegative elements. So they have the strongest attraction to electrons to form that very, very polarized bond, and also they all have lone pairs when they form covalent bonds, or at least one lone pair. So we can easily therefore determine whether a molecule has hydrogen bonding. Let's look at the three elements. If it's fluorine, there is only one possible compound, hydrogen fluoride, because once we've made that compound, there's no other possibility for fluorine or hydrogen to bond with anything else. Then when we look at nitrogen, we've got ammonia as an obvious example, but then we also have organic functional groups such as amines or amides. The one thing to notice about those is they all have at least one hydrogen attached to the nitrogen, because you can get tertiary amines and tertiary amides which have got carbons attached, and they won't have hydrogen bonding. Then when we look at oxygen, that's the most common way that we see it is water, but in our organic functional groups we also need to watch out for alcohols and carboxylic acid. So they are very commonly compared with other organic molecules that don't have hydrogen bonding. So when it comes to drawing hydrogen bonds, this can often be a 3 or even a 4 mark question, and it's quite easy to obtain full marks if you know what the examiners are looking for and you just include all of that in your diagram. So One thing that problem that people have is they sort of try to draw two molecules and then hydrogen bond them together. But one of the things about hydrogen bonds is the bond angle is really important between the hydrogen and the two other elements. So what we're going to do, instead of trying to draw two water molecules and then fudge it afterwards, I'm going to draw the hydrogen that's attached to the oxygen. And then I'm going to make sure that my other oxygen on the other molecule is in a direct line with those two, so that the bond angle around that hydrogen is 180 degrees. We also said that the lone pair is important in hydrogen bonding. Remember, the lone pair is forming an interaction with that hydrogen. So we want to draw at least one lone pair on that oxygen, but it has to be pointing towards that hydrogen. Then we actually represent our hydrogen bond, which is normally just with 3 little dashes. And then the other thing that's important, of course, is the reason this interaction is here is because of the dipole. So as a minimum, again, I'm going to put the dipoles on those 3 atoms. So those 3 are the key, and the other parts of the molecules we can just put in after we've got that bit right. So I'm going to put another hydrogen in. I've sort of tried to represent that 104-degree angle, but it's not 100% necessary. So I've just lined up my water molecules. I could put lone pairs on the other oxygens. I could put dipoles on the hydrogens, but it's not actually 100% necessary. If in doubt, of course, put them all in, but just be careful, because sometimes when we have other things like ethanol or something like that, people start to put too many dipoles in when they start putting them on carbons and CH bonds. So let's have a look as if it was something more complicated than water, which it often is, like ethanol. I'm going to do exactly the same thing. So ethanol is an alcohol with an OH group, so really it's only the OH that I'm worried about when it comes to hydrogen bonding. So I'm going to do that same structure. I'm going to draw those same dipoles, put in the lone pair, put in the hydrogen bond, and now go, okay, what's the rest of ethanol? Well, it's just 2 carbons joined together. I could display them if I wanted to, and in fact most students, certainly early on in organic, would rather just draw the whole thing, and therefore I'm going to do that at this angle. And don't forget the other H on that oxygen there. And now I've drawn 2 ethanol molecules. So the other angles are not important, it's the angle around that hydrogen. That is, think of the hydrogen as in a little tug of war between the 2 oxygens. In a tug of war, you don't stand at random angles, you stand directly opposite the other atom. Okay. Because hydrogen bonds are the strongest intermolecular force, they have a really big effect on boiling points. And our best evidence for this is when comparing the boiling points of the hydrides, so the compounds containing hydrogen, of elements from groups 5, 6 and 7. And this graph also shows from group 4. So for the elements below period 2, so starting, we've got period 3, 4 and 5 on this graph, the elements there, their hydrides gradually increase in boiling point as you go down the group. So this is a relatively simple explanation. It's due to the size of the molecule getting bigger, so there are more electrons in those molecules as we go down the group, and therefore stronger London forces or van der Waals forces. But the period 2 hydrides have significantly higher boiling points for groups 5 and 6 and 7. So we've got water, HF and NH3, our examples of the molecules that contain hydrogen bonding. So we can see they are much, much higher than the other 3, even when we go right down to the bottom of the group with the largest London forces. So they are far more significant than London forces. But the other thing we can also see is water is really high up here, even though water is not the largest molecule out of those three. And that is to do with the number of opportunities to form hydrogen bonds. So we said that hydrogen bonds, you need a hydrogen attached to an electronegative element, and that interacts with the lone pair on the electronegative element of the other molecule. So how does this relate? Well, ammonia has got one lone pair and 3 bonds to hydrogen. So it's got 3 bonds to hydrogen, but per molecule, one of those lone pairs can donate and form a hydrogen bond to another hydrogen, and one of those hydrogens can therefore interact with another molecule of ammonia. But because of the ratio of only one lone pair to 3 bonds, you don't get as many, and the same opposite problem for hydrogen fluoride, which has 3 lone pairs and 1 bond to hydrogen. So those two can only form 2 hydrogen bonds per molecule, one of the lone pairs and one of the bonds, because the ratio is not right to form any more than that. But if we look at a water molecule has got 2 lone pairs and 2 bonds to hydrogen. And what that means is it can form up to 4 hydrogen bonds per molecule. Now, it does not actually form always each water molecule 4 hydrogen bonds per molecule, and we'll look at that when we look at the properties of water later in the video. But also, that is the reason that water has these very, very unique properties. HF and NH3 are still gases at room temperature, but water's got a boiling point of 100. So clearly that extra ability to hydrogen bond is very, very significant. Let's just talk about other molecules and effect on boiling point, because we often get questions about hydrogen bonding in organic compounds. So ethanol has a boiling point of 78.5, but the isomer methoxymethane has a boiling point of minus 24.8. So just that one opportunity, one OH group, is having a difference of over 100 degrees. We could also compare ethanol with ethanal, and that's actually a more common question because aldehydes and alcohols are very commonly compared in questions. They come up in the same reaction when we oxidize an alcohol. So another big difference, and that is because obviously the aldehyde cannot form hydrogen bonds. Hopefully it's obvious looking at the molecule there that basically all of the hydrogens, that CH is no different to the other CHs. It's not polar, so we don't have a hydrogen that can interact there. But you also need to just be careful because of course you don't always get the displayed formula. You might get a structural formula. And one thing to quickly spot about aldehydes is that they would be written CHO and not OH. And that's a nice clue that tells me that that's not an OH functional group. It's not an alcohol. It's really important when we compare molecules with their types of intermolecular force that they have a similar size. Otherwise, it's not a fair comparison. So if I look at ethanol, you might think, oh, I'm going to compare it to ethanoic acid because they've got the same number of carbons, so that's a fair comparison. But ethanol has an MR of 46 and ethanoic acid has an MR of 60. That's not a fair comparison because yes, they've both got hydrogen bondings, but ethanoic acid has also got a much bigger molecular mass, more electrons and stronger London forces. So they need to be similar size, not exactly the same, just a similar molecular mass will give you a similar number of electrons. So actually, I could compare the alcohol with the aldehyde because there's only a small difference because you're just taking 2 hydrogens off to make the aldehyde. But then actually if I wanted a fair comparison with propan-1-ol and propanal, if I wanted to look at a carboxylic acid, I would choose ethanoic acid. And here you can see the effect again of being able to form more than one hydrogen bond, because Propanol, obviously no hydrogen bonding, much lower boiling point. Propan-1-ol can form potentially a couple of hydrogen bonds per molecule. Ethanoic acid has also got the C double bond O, and we'll come back to carboxylic acids and their ways that they can form hydrogen bonds with themselves later. We also need to look at the effect of hydrogen bonding on solubility, and particular in water. So water forms very many strong hydrogen bonds between its molecules. And solubility is really a comparison with the type of bonds we need to break in the solvent and in the solute, so in the molecule or compound we're dissolving, and also the type of bonds that we can form between the water molecules and its solvents. So for a molecule to dissolve, we have to break those hydrogen bonds between water molecules and push them further apart in order to kind of insert another molecule. To be able to do that, you need an organic molecule, because most of the time these questions are about organic molecules, that can form hydrogen bonds with the water, because you break hydrogen bonds between water molecules, but then you make new hydrogen bonds between the water and the organic molecule. And this means that actually we don't even talk about necessarily solubility, we talk about miscibility, and that's when two liquids can mix together. So for example, ethanol is what we would say completely miscible with water. It means that we could have a mixture that was 90% water and 10% ethanol, but we could also have a mixture that was 90% ethanol and 10% water, and they would still completely mix together. So that's quite important, but if we have a longer organic molecule with only maybe one opportunity, one OH group or one NH2 group, then it isn't necessarily going to be as soluble as you think. So don't always look at the hydrogen bonding and think, oh yeah, it's got hydrogen bonding, it's soluble. We can see from this table actually how quickly this difference comes up. So ethanol, methanol and propan-1-ol are completely miscible. The minute we get to 4 carbons, we can now only dissolve 0.11 moles in 100 grams of water, and this number is dropping off very steeply as we get a longer chain, and that's because this entire section of the molecule can only form London forces or van der Waals forces with water, and they are very, very weak compared to hydrogen bonds. So I'd have to break all those water molecules apart in order for that long hydrocarbon chain to fit in there. Okay, another thing to think about is that you have some molecules that contain a CO bond, like aldehydes. They can form a hydrogen bond with water even though they don't form hydrogen bonds on their own. So small aldehydes and ketones are also going to be miscible or soluble in water. So for example, propanone, which we use in nail polish remover, is fully water soluble or miscible. And the reason for that is, although it doesn't have an H attached to an O, it does have a strong polar bond. It has an oxygen that has a lone pair, and again, remember when we're drawing these kinds of diagrams, we don't worry about like the angle to, like the lone pair is just going to point to that hydrogen, and they're going to be, this time it's the C, the O and the H. So it's the O, the H and the O on the water that are in a straight line. So this is my 180 degree angle, and this is my relevant dipole on the water molecule. So sometimes you can get things that form hydrogen bonds with water, but even though they don't form hydrogen bonds on their own. So that's when you get a compound that is lowish boiling point compared to things that do have hydrogen bonding, but does mix with water. One little point, because this comes up loads in organic chemistry, charges versus hydrogen bonds. So we said that if it's got hydrogen bonding, it might be able to mix with water, but it does depend on the rest of the molecule. Now, benzene rings are very large non-polar parts of a molecule. So phenol and aminobenzene are relatively not that good at mixing with water. They are not that water soluble. So don't see an OH or an NH2 and immediately assume that it's all good for hydrogen bonding. But what both of these compounds can do is react with bases or acids to form a charged species. So phenol is acidic, and if I add in some hydroxide ions, some sodium hydroxide or potassium hydroxide, it will form the phenoxide ion with a negative charge. Carboxylic acids will also do this. So carboxylic acids will react to form the salt, which also has a negative charge on the oxygen. And this is going to be much, much, much more soluble. So ionic things trump hydrogen bonds. Don't always think of hydrogen bonds as being the best of everything. Ionic things are going to be more soluble than something that has hydrogen bonds. So even though I've taken the hydrogen off and I can't form any hydrogen bonds, it will still be more soluble. Another thing that can happen is that amines, so our NH2 group, if I add H+, hydrochloric acid or something like that, I'm going to form the ammonium ion, and that has a positive charge, so again that is much more soluble. That comes up sometimes in questions about how we separate out a compound. So for example, if I had that NH3+ ion, it would be totally water soluble and I wouldn't be able to separate it from my solution because it would be water soluble. If I add some alkali to reverse the change, I could go back to the NH2 and that might come out as a solid because it was less soluble, and I could therefore filter off and remove my product. Very small point about dimers, just because it sometimes comes up, that carboxylic acids, because of the shape that we have here between the C double bond O and the OH, can sometimes form molecules called dimers, which are two molecules that are hydrogen bonded together. So di just means two and mer just means two parts. So there are two molecules joined together. This can actually increase its boiling point because we've effectively doubled its molecular mass and given it more ability to form stronger London forces. And I've seen it in questions where they maybe talk about this peak coming up in the mass spectrum. Now that will only happen if the mass spectrum is done in a particular solvent where they do tend to join together. But it's something to look out for, that when you see an unusual mass that is double, it's because the molecules have been able to bond together in some ways. And in some specifications, you will also see this kind of interaction happening. You have to know about the details between the bases in the middle of the DNA molecule. And again, it's a lining up so that the H on the OH or the NH of one molecule then interacts with the O, and it can be a C double bond O. So again, this is just another example. It's the C double bond O that is sometimes forming the hydrogen bonds and not just the O on the OH group. The very last thing we'll look at is the unique properties of water. It's got a bit of crossover with some biology syllabuses as well. So we said that water is particularly unique because it's able to form up to 4 hydrogen bonds per molecule, and it doesn't usually form 4, but it does normally form a lot, and they are very strong. So obviously there's a very high boiling point. We've talked about that already. So very strong intermolecular forces require a lot of energy to overcome. You also have these properties called cohesion, which means that the molecules in water stick together very strongly, and surface tension, which is basically the same idea, but at the surface of the liquid, the molecules stick together very strongly. These are important biologically because cohesion is all about how capillary action works. So when you have transpiration stream and the water molecules are coming off the leaf at the top of a very tall tree, the reason that the water can get pulled up is because they stick together so strongly. So as soon as some water evaporates, the rest of the water molecules are pulled up because they're sticking to those water molecules. And we also have a very high specific heat capacity, which we use when we do calculations with enthalpy changes. So water takes a large amount of energy to raise its temperature. And again, that is because of this ability that you need a lot of energy to overcome those intermolecular forces. And then the final one is that ice is less dense than liquid water, which means that ice will float on water, which is highly important for life, because otherwise things would just freeze solid all the time. And so this idea of ice being less dense, why is that? We need to explain it using hydrogen bonding. If you look at this diagram of the water molecules at the moment, there are some pictures of hydrogen bonds. Water can't form the maximum number of hydrogen bonds as a liquid. The water molecules are tumbling around each other in different orientations, and we said that hydrogen bonding has specific angles. So what happens is, as the water molecules cool down, they are losing energy, and the most sort of energetically favourable state for them to be in is to form the maximum number of hydrogen bonds with each other. So this happens below about 4 degrees. The water molecules will now have slowed down to the point where they can arrange themselves in a much more open structure. And in this structure, it's a little bit exaggerated. Okay, so the gaps between water molecules are not this big, but the water molecules, you can see, are actually able to form the maximum number of hydrogen bonds. You cannot see 4 bonds in this picture because it's not 3-dimensional. You can see that there'll be certain hydrogens or lone pairs on the oxygens that are not actually involved. But you get this sort of hexagonal lattice structure, and that has gaps in it, which means that there's no water molecules in those gaps. And that is why ice is less dense than water, because there are fewer molecules per unit volume. This is exaggerated compared to the previous picture. Obviously, it's not that big a difference, but it is significant. It's important because it means that icebergs don't sink to the bottom of the ocean. It means that ice forms on the top of a pond and then insulates the rest of the pond and stops it from freezing. And it also means that air gets trapped in those little pockets in ice, which is one of our ways that we can find out about the atmosphere from millions of years ago.